Okay, for this lecture, the goal will be to show that over the complex numbers, any operator will always have at least one eigenvalue. And another one would be to show that there exists a basis which makes the matrix of T to be upper triangular. Okay, so to begin, we have to introduce a polynomial of operators. So let's think about what this is. First, let's define T to the M as T applied to itself many, many times. So M times, okay? Since it's an operator, so you can't do this with generic maps. If something goes from V to W, then you can't compose T to T because unless W is a subspace of V. In that case, that's okay. But otherwise, when you apply T to any vector, now it belongs to W, and now you can't apply T anymore, right? But if it's a operator, then for any V, TV still belongs to V, so it makes sense to apply T twice, right? And that one is by definition written as T squared of V. Okay? So we can take T to any power if it's an operator. And not only that, suppose you have P of Z as A0 plus A1Z plus da 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 AN Z to the N. I wrote this in an increasing order because it's easier for me to have the index of the coefficient match with the exponents, okay? So in that case, we define P of T as A0I plus A1T plus A2T squared da 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 AN T to the nth power. Okay? That makes sense, right? Oh, by the way, you could also take negative powers too, because if T is invertible, then you can even define T inverse, right? So in that case, negative powers will be defined as well. If T is not invertible, then you can't talk about negative powers. Okay, so an example would be, e.g., example. Suppose, just think of PZ as, say, 3z squared minus 2z plus 1. Okay. And then, let's say Q is another, let's say QZ is a polynomial on C. Then what is P of D applied to Q? See. Well, what's P of D? It's 3. Okay, first of all, what do I mean by D? I mean the derivative operator, okay? Yeah. So D squared, that means you take the second derivative minus first derivative. And for constants, I'm supposed to put identity, right? So this is being applied to QZ. So the result will be 3Q double prime of Z minus 2Q prime of Z, and then plus Q of Z. Okay. Now, you've heard over and over again how in the world of matrices, commutativity doesn't work, right? And in fact, if I had two different operators, s and t, we can't say s times t is same as t times s. That's usually not true, right? However, for t times t is t times t. I mean, if you only have t and I commutes, right? So if you only talk about things that look like this, then we can commute them. So I want to talk about that. So 5.19, if PQ are from P of F, then PQ, something that's different from just a regular vector space than this polynomial space is that polynomial space has product of vectors, where the usual vector space do not have products of vectors, right? Dimension 3 is like the only unique one. Dimension 3 has cross products, right? And that one, you can take two vectors and do a cross product, it gives you another vector. Sadly, that's not commutative. This space, it's an infinite dimensional vector space, and it also has a product of two vectors that's commutative, right? And we define PQ is defined as PQZ is equal to PZQZ. Okay. Okay. So now we have 5.20, 5.20, which is PQT is same as PTQT. Now this is a bit confusing. See, this is not a regular multiplication. This is a composition of functions, right? So when you have here, it's really you have an operator and another operator, and in between there's a composition of functions. Okay, be careful. You might think, like, isn't that obviously true? But it's not. The right side is a composition of two functions, whereas over here you have a product polynomial multiplication between two polynomials, and then only after that you're plugging in t. That's what it means. Okay, so to clarify that, let's try to write it like this. What I'm trying to say is, if you take PZ QZ, and then you plug in Z as T, okay? That's this left side, right? I'm saying that this is same as PZ, where Z is replaced by T, and then multiplying it by PT, PQZ, where Z is now replaced by T, okay? And the operation between these two is a function composition, whereas the operation between these two is a product of two polynomials. So now this doesn't seem like trivial at all, right? So let's try to prove that. Well, how do we actually multiply polynomials? That's a bit hard to say. If I say P of z is summation of a k zk, okay, and then q z is summation of bi zi, okay, where I is not the imaginary number, but it's the index going from 1 to 0, starts from 0. So, and I'm intentionally refusing to write down where it begins and where it ends because it gets tricky. They both begin at 0, but they end at some degree. So if this is degree n polynomial and this is degree m polynomial, it will be n and m, right? Okay. So now, what happens if we multiply these two? Pz qz is summation of a k zk times summation of b I zi, and then this can go inside the summation, and then this can also go inside. So you end up with a double summation of ak bi z of k plus I. That happens. Okay. And therefore, if I have pz qz, z replaced by t, that's going to be double summation of ak bi z t k plus I. All right. But then you can check if you do the same thing on the right side, you get the same thing. Yeah, and by the way, by definition, t to the 0th power is identity, okay? Regardless of whether t is invertible or not, that's going to be our convention. So p of t would be summation ak t to the k, and q of t would be summation of bi t to the I, and therefore if I do pt qt, it's the same calculation, summation of ak tk summation bi ti. So it's like this, but then you can bring this inside here, so that summation ak tk is, oh, sorry. This is now multiplied by bi ti, but then now you can bring this inside here, so that's a double summation of ak bi tk ti, which is like that. Okay? So you get the same thing. And all of this is true because t and I are commutative. Okay? So yeah, just to explain why we're trying to do this. Suppose you had like 2 variable polynomials, something like this. So that it's like you have 3x squared plus 4xy plus 5y to the cube, something like this. Okay. Suppose you had this. Okay. Then you can also think about TS like this. If you have TNS, no, T, you can definitely think about something like this, right? Yeah. But if you define multivariable polynomials and try to do something similar, then that kind of thing wouldn't work because S and T need not commute. This kind of thing only works because T commutes with itself, and T also commutes with identity. Identity commutes with anything. Okay. So you might think that what I'm writing down is like unnecessarily long. In a sense, yes. Maybe we could just say in words that T commutes with itself and T commutes with I, so therefore that always works. Maybe saying in words might be enough. Yeah, so you have this, and then the outcome of this is that you can also say P of T, Q of T is same as P, Q of T, P of T. Okay. So you have this. And this result is saying that if you have a T and you build polynomials of that T, then you have this family of operators where they all commute. That's what it's saying. Okay. See, P of T is an operator, Q of T is another operator. They are distinct operators, right? But they commute. So if you view it that way, this is slightly less trivial, right? But this is true because this is same as PQT, right? Where PQ is a polynomial multiplication, and in the world of polynomials, of course, two polynomials commute in multiplication, right? So you can say this is same as that, but that's same as this. So this calculation says this immediately, right? Okay, so that's somewhat needed. In other words, when we talk about polynomials of operators, we don't have to be careful about commuting things. That's basically what we're establishing here, okay? Okay, so in 5.21, let V be a complex vector space. In other words, it's a vector space over the complex number C. Then any T that's an operator on V has at least one eigenvalue. All right, so here's an interesting proof. I think this proof is pretty neat. So take any V non-zero, V in V. Okay. Consider V, TV, all the way up till T n V, where n is the dimension of V. Oh, I should have said that it's a finite dimensional. Okay? It's a finite dimensional one. Now, what's the length of these vectors? How many do you see? T0, T1 until n, so it's n plus 1. Okay. Since the length is n plus 1 inside and dimension V is n, this list must be linearly dependent. What does that mean? That means there exists A0 times V plus A1 times TV, AN times T and V equal to 0 for A0 through AN, not all zeros. Okay? All right. So let's assume that the AN could be 0, right? And the previous one, the next one could be 0, but there's like some m where m is the highest number, where after that it's all 0. Okay, so this means there exists an m between, well, it has to be at least 1 through n. See, if all of A1, if A1 through AN are all zeros, then that doesn't make sense, because you just have A0 times V, and since V is non-zero, A0 is forced to be 0. If A0 times V is 0, then A0 is forced to be 0. So m should be at least 1, such that A0V plus A1 TV plus AM T MV is equal to 0 with AM non-zero. Okay, so it's like m is the largest number where AM is non-zero. After that, it could be 0. M could be n itself, which means this is non-zero, but if this is 0, there should be some place that happens. But now consider, since PZ is degree m polynomial, the fundamental theorem of algebra says that this one has m zeros, right? M zeros, not all of them equal to, no, m zeros counting multiplicities. Okay, some of them could be equal. Yeah. So that means P of Z is equal to AM times Z minus lambda 1, Z minus lambda M. Some of the lambda k's can be equal to each other, that doesn't matter. All I care is that you have M of those. Right? So that P of T is same as this guy. Okay? P of T is A0V. Oh, sorry. P of T is A0I plus A1T plus AM T to the M. And since we know that you can, if you have a polynomial multiplication, like you can take the multiplied version and replace z by t, or you can also take individual z's and replace by t and constants by I, and then multiply them. They're the same, right? That's what we proved essentially in the previous theorem. So this is going to be same as AM times t minus lambda 1I times t minus lambda 2I t minus lambda mi. That's what we found out, right? Now, what does that mean? P of TV is this applied to V, which is exactly this one, right? So it's 0. Okay? T of V equals to 0, so that AM T minus lambda 1I all the way up till T minus lambda mi applied to V is equal to 0. Is that okay? Right? Okay. Because this is same as this guy, which is equal to 0. That's what I'm saying. But if this is true, then at least at some point, the null space of t minus lambda k I is not equal to just the trivial one, right? And the argument goes like this. Maybe this is 0. If this is 0, then the null space of this is just this, right? Suppose this is not 0, then just call this as V1. And then the next one should kill this, right? If it kills, then this V1 is in the null space, right? If not, just go to the next one. If if all of these have trivial null spaces, then there's no way that this could be equal to 0. Okay? Unless AM is 0, but we assume that AM is non-zero, right? So there should be some k where null of t minus lambda ki is non-zero for some k. Okay? And we also know that if t minus lambda ki is not injective, that's equivalent to saying that lambda k is an eigenvalue of t. So the proof is done. Okay? And let me ask a question just to be sure you understood how this proof works. Where did we use the fact that the base field is C? Can you think about that? Where did we use the fact that the base field is C? It's here. Okay. Because can polynomials be factored into linear factors over R? Not always, right? So that's the exact example that we were talking about. X squared plus 1 cannot be factored over R, but over C you can factor as x plus I times x minus I. Right? The reason that we weren't able to find the eigenvalue for the rotation example was exactly this. We ended up with lambda squared plus 1. That one doesn't have solutions, right? But lambda squared plus 1 can be solved over C. That's why it has a solution. So that's exactly this. I should first say something, okay? the following are equivalent. So let's say there's a basis v1 through vn, and t is a linear operator on v. Then saying that the matrix of t with respect to this basis is upper triangular is same as the following. One is t vj is in the span of v1 through vj, and then c span of v1 through vj is an invariant subspace for T. Okay, so these are equivalent. And the purpose of this is so that we want to show that there exists, for any T, there exists some basis so that the matrix is upper triangular, but trying to argue that is hard, so we're going to, instead of proving this, we will prove this or that. Okay, that's the way we're going to work. By the way, what does upper triangular mean? Well, if you have a matrix, the matrix of T should be a square matrix because it's an operator, and over here, this is called a diagonal of the matrix. Hopefully you know that already. This is never called the diagonal of a matrix. It's only this one is called the diagonal of a matrix. Okay, maybe that's called an anti-diagonal sometimes, but when you say diagonal of a matrix, it's never this one. It's always this way. Okay, so that's the diagonal. And upper triangular means you may have something here, and you may have something here as well. But all of the things below the diagonal must be 0. That's what upper triangular means. Okay, so that is equivalent to saying this, which is equivalent to saying this, and then that's same as that. Okay. All right. So it's just a matter of understanding what this matrix representation means. So maybe we should just work with something really simple. Let's say you have just 3 vectors, okay? So if you have v1, v2, v3, and let's say t of v1 is a11 plus a21 a31, okay, and then t of v2 is a v1 a12 plus a22 v2 a32, and t of v3 is a13 a23 a33. And if that's the case, then what's the matrix of T with respect to v1, v2, v3? Well, you just simply take these coefficients and put them vertically, right? So all of the numbers that you go across has to be written vertically. So it's like A11, A21, A31, and then A12, A22, A32, and then A13, A23, A33. Okay. This means that. Okay. So once you know this, then what does it mean to be upper triangular? Well, that means upper triangle means these are 0, right? This has to be 0. So what does that mean? That means these have to be 0 and that has to be 0. Okay? And that's it, that's the proof. Because T of V1 is definitely in the span of V1, right? T of V2 is in the span of V1 and V2. T of V3 is in the span of V1, V2, V3. That's exactly this statement, right? Yeah. And also, if this is true, then if you have V1 and V2, the subspace spanned by V1 and V2, if this is true, it will be an invariant subspace, right? Is that good? So, if this is true, then let's take any vector in the span of V1, V2, which means U is equal to C1 V1 plus C2 V2, right? But then T of U would be C1 times T V1 plus C2 times T V2 because T is linear, and then C1 times A11 V1 plus C2 times A12 V1 plus A22 V2. So again, that's equal to C1 A11 plus C2 A12 V1 plus A22 V2, and therefore this belongs to span of V1, V2. So if I call this vector space U, what did I just prove? I took any element in here, and the result still lies in here. So that means T of U belongs to U. It's a subset of U. So U is indeed the invariant subspace. Okay. So this implies this, if you think of this example, right? And then if this is true, again, it has to look like this. So the same as that. So I mean, the book writes a lot just to say this, but if you think about it, if you think about what the matrix means, then it's just a different way of rephrasing what's obvious. Okay? So hopefully that makes sense. So just have this idea and read the proof in the book. It should be very straightforward. All right, so we're focused on diagonalizing a matrix, right? And at the end, you will see that it's not possible for any matrix T, and we will be able to talk about a subclass of matrices called normal that allows you to find some orthonormal bases you can diagonalize it. But in general, that's not true. That's why we end up with something called Jordan normal form. And this is like a preliminary to getting there. So Jordan normal form is like you have eigenvalues on the diagonal, and then you might have like one at some point in off diagonal some places, and every time you have a 1, 1, the eigenvalues for those has to be the same, and then 0 everywhere. It's an upper triangular matrix where the diagonals are eigenvalues, and you have some zeros. So it's like a band matrix. So only at the diagonal and one above you have non-zeros, and everywhere else is 0. That's like the best you can hope for. For any matrix, you have something called Jordan normal form. And this is a weaker one because we're not saying you can have this, you can have something else. Okay, so this is a weaker kind of theorem which says you can pick a basis to make this upper triangular. But once you have upper triangular, then a lot of nice things happen, so that's still desirable, okay? So let's try to show this. Proof. So we use induction. With dimension of V equals to 1 as the base case. So for the base case above is true trivially. Because if you have a one-dimensional vector space, then the matrix is 1 by 1. Any 1 by 1 is, by default, it only has a diagonal element, so it's upper triangular. So it's true trivially. Now, suppose dimension of V is bigger than 1, and the induction hypothesis is that induction hypothesis is that any vector space with less dimension has such basis. Okay. So let's think about that. Now, I forgot to say, V is a vector space over C. Okay. If it's not over C, this is not true. Okay, you need an eigenvalue to carry on. Okay, so let lambda be an eigenvalue of T. Okay. We already proved that over C, any operator has an eigenvalue, at least one eigenvalue. Okay. Let U be the range of T minus lambda I. Now then, U is a invariant subspace of T. So let's see why that is so. For any U in U, you see that T minus lambda I, T applied to U is equal to T minus lambda IU plus lambda IU. Right. That's true. Seems like I'm writing nonsense, but look, this is in the range of T minus lambda I, right? This one is in the range of T minus. And this one is same as lambda U, and because range is a subspace, any scalar multiplication is again in U. Okay? So this is still in U because U is closed under scalar multiplication. Okay? It's a subspace. So that shows that the resulting TU is in U, right? Because U is also closed under addition, vector addition. So since both of these are in U, some of these two are in U. So that shows that T of U is a subset of U, which means U is an invariant subspace. Now, why do we want this? We want this because we can restrict T under U. Okay, so I can talk about that. But then, notice that because value, we know that t minus lambda is not surjective, right? Since it's not surjective, the range is not all of v. So this must, it has a less dimension than v, okay? Which means I can use the induction hypothesis to say that use induction hypothesis to find u1 through um, okay, where m is the dimension of u, okay, such that this is upper triangular. Okay. You know that that's equivalent to saying that t u of u I, u k is in the span of u1 through uk, right? For k between 1 through m. Okay, that's what upper triangular means. Now what you do is now extend u1 through um to a basis u1 through um, v1 through vn for v. Okay, and that's possible because, first of all, u is some dimension less than v, but we don't know how much. Okay, so if the difference between u and v is dimension n, we need to attach n more vectors together, basis, right? That's why I'm writing down v1 through vn. Okay, so we have a basis. Now let's try to see what we can say for t of vk. Well, t of vk is t minus lambda I vk plus lambda vk. Same trick as before, right? But look, this is again in the range of t minus lambda I, which is equal to u, right? So these guys are in the span of u1 through um. Agreed? Okay. But then you have lambda vk, so this is again in the span of u1 through um and v1 through vk. Okay, because this it's really we actually don't use any of these. In actuality, we just need these guys because it's in here plus some lambda times vk. That's all we need. Right? And then you put these back. Being in the span of this means it's also in the span of this. It doesn't hurt to have more things, right? So now you have that. That's equivalent to saying that it's upper triangular. Okay? So that's it. That's the proof. Let's say we took some arbitrary linear operator and found a basis that's guaranteed by our previous theorem to make this matrix upper triangular. Okay? Then the diagonals of this upper triangular matrix, which we're going to call lambda n through lambda n and then 0, these have some important consequences, and the first consequence is that if none of these are 0, then this is invertible. Okay. Now, this is kind of obvious. Again, if you write down a 3 by 3 matrix, so let's just do this one: lambda 1, lambda 2, lambda 3, and I'll just put A, B, C, 0, 0, 0. Okay. So let's say m of t is this. Okay. Let's see. And if the basis that produces this matrix is v1, v2, v3, okay, tell me what t of v1 is. You read by columns, right? So it'll be just lambda 1 v1. Okay. T of v2 would be lambda 2. No, what is it? A times v1 plus lambda 2 v2, right? And then T of v3 would be b v1 plus c v2 plus lambda 3 v2, right? v3. So what that means is that if I take T of 1 over lambda 1 v1, that gives you v1, right? And then you can also do T v2 minus a times 1 over lambda 1 v1 v2 divided by lambda 2. Okay, what does that give you? This gives you minus a v1, and this gives you, no, should I be doing, oh, sorry. Should be like this. Okay. Then, so let's see what that gives us. That's TV2 is a v1 plus lambda 2 v2 minus, this one gives you v1, right? So a times v1 divided by lambda 2, so that's equal to v2. In other words, it's stupidly easy to find the inverse of this. What's the inverse of this? You can just do back substitution, right? If you have an upper triangular, the inverse is really easy to do. It's just, you can just do it by back substitution. It's like, if you have x, y, z, then lambda 1 times x is this other one, so you can just divide by this, and you just keep back substituting, and you get the inverse for everything. So you keep doing this, then you end up with something giving you v3 as well. So what that means is that t is surjective because it produces all the basis elements in the target, right? So if t is surjective, then it's invertible. That's true in a finite dimensional space, right? So that's true. And then the immediate corollary of this is 5.32, which says these diagonal elements are eigenvalues of t. Okay? And why is that? Well, if you just simply do t minus lambda I, okay? And then you take the matrix with the thing that gives you this upper triangular. Now, the matrix of I is always lambda on the diagonal. It never changes. No matter what kind of matrix you use, the I is always 1 on the diagonal. So you end up with lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda, something like that. And look, if lambda is any one of these values, then you get a 0 on the diagonal, right? Which makes it not invertible. If it's not invertible, we learn that it's an eigenvalue. So it's a direct corollary of this.